In this video, we're going to look at standard scores. The number of standard deviations from the mean is called the standard score or z-score. You're going to hear this z-score a lot when you talk about and use normal distribution. Let's look at an example to see how this is used, why is it important. So in a school, one of your friends is 1.85 meters tall. You can see from the bell curve that 1.85 meters is 3 standard deviation higher than the mean. So the mean in the normal distribution was 1.4. If you count the standard deviation 1, 2, 3, the height of 1.85 is 3 standard deviation away from the mean. So your friend's height has a z-score of 3. So basically the z-score tells you how far that data point is away from the mean. A positive z-score will be higher than the mean, a negative z-score will be lower than the mean. It's possible to calculate how many standard deviation, 1.85, is from the mean, and the way you calculate it is that you subtract the data point minus the mean, and then you divide by the value of the standard deviation. Okay, so in this case you do 1.85 minus 1.4, this is 0.45 from the mean, and the standard deviation for this distribution is given as 0.15. So you divide the difference, the 0.45, by the standard deviation, and you get 3. So this is the z-score. That height of 1.85 is 3 standard deviations higher than the mean. So to convert a value to a standard score or a z-score, you first subtract the mean from that data point, then divide by the standard deviation. And doing that is called standardizing. So you take a normal distribution with random numbers on the bottom or whatever they represent, and by finding the z-scores you standardize, you use the standard normal distribution. In a standard normal distribution, the mean is always 0, and the standard deviations, you can see that you are 1, 2, 3 standard deviations above the mean, 1, 2, 3 standard deviations below the mean. You can take any normal distribution and convert it to the standard normal distribution. And basically that's what is done in practice. Whatever the scenario that you're working on, you convert it, you find the z-scores, you convert your normal distribution to a standard normal distribution. And the reason for that is because there are tables of probabilities and proportions that will tell you the area under the curve or the proportion under the curve for any value of the z-score. Okay, so instead of kind of finding it for each particular scenario, you standardize it and you can use one table to figure out your answer. Here's another example for finding z-scores. The Stanford Binet IQ test is scaled so that scores have a mean of 100 and a standard deviation of 16. Let's find the standard score or z-scores for IQs of 85, 100, and 125. So basically, to find the z-scores for these IQs, we use that formula. We subtract the data value minus the mean, and we divide by the standard deviation. So for the standard score for an IQ grade of 85, we take that 85 minus the mean, and you divide by 16. So do 85 minus 100, you get negative 15. Then divide by 16, we get a z-score of negative 0.94. Basically, that means that 85 is 0.94 or almost 1 standard deviation below the mean. Now for a score of 100, we take 100, that score, minus the value of the mean, which is 100, and we get 0. Divide by the standard deviation, and we get a result of 0, a z-score of 0. So that means that 100 is equal to the mean, so you're not away from the mean in any direction. And finally, for our standards, for a score of 125 to find the z-score, we do 125 minus 100, which gives us 25, divide by the standard deviation of 16, and we get 1.56. That means that a score of 125 is 1.56 standard deviations above the mean. Let's look at an image of the situation. So we had a score of 85, which is this line right here, is negative, has a z-score of negative 0.94, so it's almost one standard deviation below the mean. A score, an IQ score of 100 has a z-score of 0, so that's in the center, that's equal to the mean. And an IQ score of 125 has a z-score of 1.56, which is about 1.5 standard deviations above the mean.